Good morning, chemistry students. Here are your Chapter 9, Day 4 notes. Keep forgetting to put that word on there. We're going to start with 9.3, your limiting reagent and percent yield, and we are basically going to stop before we get to percent yield today. Again, just kind of a reminder of things you need to have as we're getting started here. You should definitely have, obviously, your outline out. You should have your periodic table with your helper sheet out. You should have your polyatomic ions you have memorized if you don't know those very well. You should have your chemistry toolkit with those 5 conversion factors from Chapter 7 and the new one from this chapter, the mole ratio. Because again, you're going to be choosing those as we work through these problems today. So, this really, again, is definitely the chemistry you would do if you were working in industry. This is the chemistry you would do if, or that you will do when you go to college and you take a college level chemistry class. This is about how much do I have to start with so that I produce the desired amount of product, right? If we're working for Dow Chemical Company, and somebody orders 1,000 pounds of some chemical that we produce, we don't want to produce 5,000 pounds of it. That's way too much. But we also can't produce only 900 pounds of it because we haven't fulfilled our order. And the way that the chemists go about figuring out how much do we have to start with so we can produce that 1,000 pounds of our product, they use limiting reagents and they use percent yield to do that. So this is definitely the chemistry that you do day in and day out in a college level chemistry class in your labs and in industry. And really this is a nice spot for us to end Chemistry 1B because it really is bringing together everything that you've learned in chemistry kind of all into one kind of type of problem. So we're going to start by talking about what is a limiting reagent, and we're going to start by talking about everyday examples. We talked about cookies and baking the other day, right? Again, if you have a recipe for cookies, and again, many of you have probably done this before, right? You have a recipe for cookies and your recipe calls for, let's say, 1 cup of sugar and 3 eggs, and it produces 1 dozen cookies. Okay, so let's say that you need to produce 2 dozen cookies. What do you do to the whole recipe and everything in the recipe? You would double it. All right, let's say you're going to make cookies and you discover that you don't have 3 eggs. You only have 2 eggs. Well, what are you going to do to your recipe? You still can make your cookies, right? You're just not going to produce 1 dozen of them. You're going to produce 2/3 of a dozen, okay? And again, you have to adjust the amounts of all your other ingredients, right? For example, with the sugar, if you only have 2 eggs, you're going to use 2/3 of a cup of sugar rather than 1 cup of sugar. So again, you have done this when you've been cooking, if you've done any kind of baking and such, if you've adjusted a recipe, okay? That's an example of a limiting reagent. If you only have 2 eggs, eggs are your limiting reagent for your recipe. Again, if you happen to have your own car to drive, whether it's provided by your parents or because you've paid for it, right? Gassing up is another example of a limiting reagent. Your tank might be empty when you go to the gas station, but if you only have $5 worth of cash in your pocket, then you can't fill up your gas tank. You can only put $5 worth of gas in your gas tank. In that case, your limiting reagent that determines how much gas you can purchase is the amount of money you have. That's another example of a limiting reagent in real life. Lastly, we'll kind of talk about sandwiches. If we assume that a sandwich should have 2 pieces of bread, 2 slices of meat, and a slice of cheese, okay? If you have 10 pieces of bread and 10 slices of meat, okay, you can produce 5 sandwiches, right? And you only need 5 slices of cheese. If you go to get your bread out and you only have 6 slices of bread, you can only make 3 sandwiches. You're only going to need, okay, 6 slices of meat and 3 slices of cheese. Again, in that case, the bread is your limiting reagent, and it's determining how much of your other reactants you need, your meat and cheese, and how many products you can produce. 3 sandwiches. So again, those are examples of when you have probably dealt with limiting reagents in the real world. Now we're going to talk about this in chemistry. So keep in mind that the balanced chemical equation is like a chemist's recipe, right? It tells you the relative amounts of all the reactants and the products that you need to carry out the reaction. Just like a recipe tells you the amounts that you need. The definition of the limiting reagent is that it limits or determines the amount of product that can be formed in a reaction. Again, when we talked about gassing up, our limiting reagent was our cash. When we talked about making sandwiches, our limiting reagent was the slices of bread we had. When we talked about cookies, eggs, that was our limiting reagent. It limits, or it's going to determine how much of our product we can actually have. One of the keys to identifying the limiting reagent is that you use up all the limiting reagent that's provided or available. So there won't be any limiting reagent left over. After the reaction. Now, that's in contrast to what is the excess reagent. The excess reagent is the reactant not completely used up in the reaction. Okay, and keep in mind when we're looking at limiting reagent, it's always a reactant. Our product is never a limiting reagent, okay? So again, our excess reagent is any reactant, or if there's multiple reactants, not completely used up in the reaction. So again, the key to this is some excess reagent is left over unreacted. So again, when we think about gassing up, right, the amount of money we have, our cash is our limiting reagent. The excess reagent is the gasoline, right? There is still gas at the gas station after we've gassed up. We don't use it all up. When we were talking about making the sandwiches, right? Again, we said the amount of bread, we ran out of the bread. There was still plenty of meat. There was still plenty of cheese. So the meat and the cheese were the excess reagent. When we talked about cookies, right, we said the eggs, if we were short of eggs, what our recipe called for, our eggs are our limiting reagent. Again, that means that everything else that we need in that recipe, we have plenty of, and there's going to be some of it left over even after we use what we need. So, limiting reagent, excess reagent, they're always a reactant. Okay, typically most of your problems are just going to have two reactants, and so you'll identify one of the reactants as the limiting reagent and one of the reactants as the excess reagent. So, how do we kind of figure this out? First off, how do you even know that you have a limiting reagent problem? Because sometimes your book isn't going to tell you that, and I'm not going to tell you that. So when you're given the amounts of all the reactants, okay, you must determine which reactant is the limiting reagent. And again, this is your clue that your problem is a limiting reagent problem, even if it doesn't say it. If you're given the amounts of all the reactants, you know, even if the problem doesn't say it, and eventually it will stop saying it, okay, you know that it's a limiting reagent problem. That first you have to decide which one of the reactants is your limiting reagent and which one is your excess reagent. Again, you have to determine the limiting reagent because whichever reactant is the limiting reagent will determine the maximum amount of product produced. So what that means for you is that you must use the limiting reagent to calculate the amounts of all products. So the best way to kind of see how this works is to look at a problem. So we're going to take a look at this with a problem, and you should have a problem already written on your outline. Your problem is example, the complete combustion of ethane. If 2.70 moles of ethane is reacted with 6.30 moles of oxygen, calculate the moles of water produced. Notice this problem doesn't say anything about it being a limiting reagent problem. How do I know it's a limiting reagent problem? Because they've given me the amounts of both of the reactants. And because they've given me the amounts of both of the reactants and asked me to calculate the amount of a product, I know it's a limiting reagent problem. Now, remember, the first thing you need to do any stoichiometric problem is a balanced chemical equation. And there isn't one for this one, so let's do this. Now, again, we have some clues here, right? They tell us it's a combustion reaction, and they give us the formula of ethane, so we know we have C2H4. Now, again, for combustion, remember, for something to burn, there's always another reactant we need, which is oxygen gas, O2. And the products of all combustion reactions are carbon dioxide and water. So again, this is bringing together the fact that you're able to write and balance a chemical equation. So now it's time to balance this. So we have 2 carbons, so we need a coefficient of 2 in front of carbon dioxide. We have 4 hydrogens, so we need a coefficient of 2 in front of water. Now we have 2 times 2, which is 4, plus 2 more, which makes 6 oxygens, so we need a coefficient of 3 in front of oxygen. So again, to check this, I have 2 carbons, I have 2 carbons, I have 4 hydrogens, I have 2 times 2, which makes 4 hydrogens, I have 6 oxygens, 3 times 2, I have 2 times 2, which is 4 here, plus 2 more makes 6, so this is a balanced chemical equation. Now again, these are story problems, so I like to summarize the information underneath my problem so I don't have to keep looking back at it. So this problem says that I have 2.70 moles of ethane and 6.30 moles of oxygen. So, step number 1 is to determine the limiting reagent. Now, I'm going to go ahead and put this balanced chemical equation here again. I'm going to kind of put it up here. So we have C2H4 plus 3CO2 yields 2 carbon dioxides and 2 waters. 2CO. And the amounts that I'm given, okay, are 2.70 moles of this and 6.30 moles of this. Now, I'm going to show you 2 ways. There's always 2 options or 2 ways to do this. You only will ever do one. I'm going to show you both ways to prove to you that it doesn't matter which way you do it, you arrive at the same limiting reagent. But you would only do one. So, option letter A. I can take my 2.70 moles of C2H4 and figure out how many moles of oxygen I need. Now, I'm going to do moles because my reactants and products are both in moles. So that's option A. Option B. Okay. I can take the 6.30 moles of oxygen and figure out how many moles of ethane I need. Again, you would never ever do both. But I want you to have both in your notes right now. But I want you to have a note in your notes that says there's two options or ways to do this, but you only do one when you actually do a problem. Okay, I'm showing you both to prove to you it doesn't matter which way you do it. You still get the same limiting reagent at the end. So hopefully these are pretty easy problems, right? Our only way to change from substance to substance is a mole ratio. So I start with my given 2.70 moles of my ethane. Moles of ethane need to go on the bottom. I'm converting it to moles of oxygen, my other reactant. And my numbers come from my coefficients. So my coefficient on oxygen is 3, and on ethane it's 1. So again, on my calculator, I'm going to take 2.7 and multiply it by 3. I want to have 3 significant figures. So 8.10 moles of oxygen we need. Now, the math isn't usually what gives people a hard time. Usually it's the kind of evaluation part. So this is how much we need. What this means is to react with all of the ethane, we need 8.10 moles of oxygen. So now I want to look at how much do we have. In the problem, we have 6.30 moles of oxygen. So the question is, are we going to run out of oxygen? Do we need more than we have? Yes, we need more than we have because we need more than what we have. Therefore, okay, oxygen is our limiting reagent. So I like to label that. I like to come back up here and say, this is my limiting reagent, so I remember. Now, remember, you would only do this one way or the other. You would never ever do both. I'm doing both to show you that it doesn't matter which way you do it. So let's say instead you had chosen to start with your 6.30 moles of oxygen. Then your moles of oxygen would be on the bottom, and you would convert that to your moles of ethane using your mole ratio. Moles of oxygen cross out. Again, in our mole ratio, it's our coefficient. So our coefficient on ethane is 1, and on oxygen, it's 3. So on my calculator, I'm going to do 6.3 divided by 3. I want 2 or 3 significant figures, so 2.10 moles of ethane that we need. Right? So again, what this is saying is to react with all of the oxygen, I need 2.10 moles of ethane. How much do we have? Well, we have in the problem, they told us 2.70 moles. So the question is, am I going to run out of ethane? No, I need less than I have. So because I need less than what I have, therefore, this is the excess reagent. So the other reactant has to be the limiting reagent. Notice it didn't matter which way I did this. I still ended up with the same excess and limiting reagent. So again, you'll never do both. I want you to have both on your outline to prove to you it doesn't matter which way you do it. You can do it one way, your friend can do it a different way. You'll still get the same limiting reagent. So now that we've done that, we actually haven't answered the question yet though, right? The question says the moles of water produced. So now we're ready to calculate the moles of water produced. So now we're going to use the limiting reagent to calculate the moles of water. Again, I'm going to put my equation up here. So we had C2H4 plus 3O2 resulted in 2 H2Os and 2 waters. 2 CO2s. I said H2Os and 2 waters, which are the same, but 2 carbon dioxides and 2 water. Again, we knew we had 2.70 moles of ethane. We know that we had 6.30 moles of oxygen. We already figured out that oxygen was our limiting reagent and ethane was our excess reagent. Now we're being asked to figure out the moles of water. So again, should I start with my 2.70 moles or do I start with my 6.30 moles? Remember, on our notes, we said, okay, we must use the limiting reagent to calculate the amounts of our product. So we have to start with the 6.30 moles of oxygen because oxygen is our limiting reagent. Moles of oxygen go on the bottom, so they'll cross out. We're calculating moles of water, so that's going to go on the top. We want it in moles, so it's nice and easy. And again, where do we get our numbers for our mole ratio? Those come from our coefficient. So our coefficient on water is 2, and on oxygen it's 3. So again, with my calculator, I'm going to take 6.3, multiply it by 2, and take that answer and divide it by 3. And I want to have 3 significant figures. So I get 4.20 moles of water. Now, the other question that sometimes these problems will ask is how much excess reagent is there left over? Well, how would you do that? To do that, you'd kind of go back here and you'd use this information. We know we're going to use this much. This is how much we have. So to figure out the amount that's left over, we would take the 2.70 moles of ethane that we have, given in our problem, subtract the 2.10 moles of ethane we need or use, and figure out that we have 0.60 moles left over. Now, if by chance you calculated your excess reagent this way, then you would have to do this calculation to figure that out if you had a question about how much excess reagent is left over. So, we've done one. Let's practice this one more time. So we have hydrogen gas can be produced in the lab by the reaction of magnesium with hydrochloric acid, also known as hydrogen chloride. Identify the limiting reagent when 6 grams of hydrogen chloride reacts with 5 grams of magnesium. So again, first thing I need is my balanced chemical equation. I'm producing hydrogen gas by the reaction of magnesium with hydrochloric acid, which is hydrogen chloride. That's an ionic compound, so hydrogen +1, chloride -1, so nothing to do. Now, this is a single replacement reaction, right? So the other product isn't mentioned here, but when I'm balancing my equation, I need it because it's going to be important. And that's going to be magnesium and chloride, which is an ionic compound, so Mg +2, Cl-, so it's MgCl2. So to balance this, I need a coefficient of 2 on my hydrogen chloride. Now, again, this problem says that I have 6 grams of hydrogen chloride and 5 grams of magnesium, and it's just the first part here is just asking me to identify the limiting reagent. So again, remember, I have 2 options, right? Option A, I can take the 5 grams of magnesium and figure out how many grams this time of hydrogen chloride I need. Why grams? Because the amounts are given in grams both times. Right? Option B, okay, is I can take the 6 grams of hydrogen chloride and figure out how many grams of magnesium I need and do that comparison. Again, you would never do both. I'm going to do both because I want to prove to you again and show you again that it doesn't matter which one I start with. Okay, so if I start with my 5 grams of magnesium, right, my only way to change from one substance to another is my mole ratio. So I have to convert these to moles. Well, that's good because I have a tool that has moles in it. It's called molar mass. So grams of magnesium to moles of magnesium, that's my molar mass. Now I can use my mole ratio, moles of magnesium to moles of hydrogen chloride. Ooh, and I gave myself more room for this. Then we'll take moles of hydrogen chloride, and we have to use molar mass to convert it back to grams of hydrogen chloride. And I'm going to go ahead and put that other option on the next slide so that I have a little bit more room here. Okay, so we'll still do that. I'm just going to do it on the next slide. Now, numbers. Right, so remember this was molar mass. This is my mole ratio. Again, these should be on your chemistry toolkit. And this is molar mass again. All right, so where do I get my numbers for molar mass? If you're not sure, look at your chemistry toolkit, right? The number in front of moles is always 1. The number in front of grams comes from our periodic table. I want to use at least 3 significant figures. So magnesium's mass is 24.305, so I'm going to use 24.3. Mole ratio. My mole ratio numbers come from my coefficients in my balanced equation. So my coefficient on hydrogen chloride is 2, and on magnesium it's 1. And molar mass again, the number in front of moles is 1, and the number in front of grams comes from our periodic table. So we said magnesium was 24.305, and hydrogen is 1.0079, and there's just, I don't want magnesium. Holy smokes. I want chlorine, right, because it's HCl. So chlorine is 35.453. I'm going to add to that hydrogen, which is 1.0079. And I get 36.4609. I want 3 sig figs, so I'm going to say it's 36.5. Now, again, how do I do this on my calculator? Right? I'm going to put in 5 times 2 times 36.5. And I'm going to divide that answer by the 24.3. And again, I want to use 3 significant figures, so I get 15.0 grams of hydrogen chloride that I need. Now, I have in my problem, okay, 6 grams. So, am I going to run out of hydrogen chloride? Yes. I need more than I have. Therefore, hydrogen chloride is my limiting reagent. Again, let's look at option B. Okay. right? Option B was that I could start with my 6 grams of hydrogen chloride and figure out how many grams of magnesium I need. So again, if you opted to do this way, you'd start with your 6 grams of hydrogen chloride. Now your masses won't be any different, so it's still molar mass, which is 36.5 grams of hydrogen chloride to 1 mole of hydrogen chloride. Then I'm going to use my mole ratio. Moles of hydrogen chloride are on the bottom this time because they're on the top. And this time I'm going to moles of magnesium. And then moles of magnesium will be on the bottom. Grams of magnesium, so this is my molar mass of magnesium. Again, this will be the same as it was, so it was 24.3 using our periodic table. This is our coefficients. So our coefficient on magnesium was 1 and hydrogen chloride was 2. Now, again, how do I put this in my calculator? 6 times 24.3. I need to divide that answer, and I'm going to have to use parentheses because I need to divide it by both of those numbers. So 6 times 24.3 divided by 36.5 times 2. And I get 3 sig figs. I get 1.997. So I'm going to say it's 2.00 grams of magnesium that we need. Now, how much do we have? We have, in the problem, we have 5 grams of magnesium. Therefore, we won't run out. Of magnesium. Therefore, magnesium is our excess reagent, and oxygen is our limiting reagent. So again, it doesn't matter which way we do this. Either way, we get the same, okay? Sorry, and I said oxygen, but it's not oxygen, it's hydrogen chloride. But either way, right? Hydrogen chloride is our limiting, magnesium is our excess. So, now we're ready to answer the actual question that this problem had, which was how many grams of hydrogen can be produced. So again, our equation is, okay, Mg plus 2HCl yields H2 plus MgCl2. We had 6 and 5. So we had 5 grams of this. We had 6 grams of this. We're asking to figure out how many grams of this can be produced. We determined that our limiting reagent was our hydrogen chloride and our magnesium was our excess reagent. So, how do we calculate this? Again, remember, we must use our limiting reagent. So, we're going to start with the 6 grams of hydrogen chloride. And again, remember, our only way to change from one substance to another is with our mole ratio. So we need to use our molar mass to convert grams of hydrogen chloride to moles of hydrogen chloride. Moles of hydrogen chloride have to go on the bottom. Moles of hydrogen are going to go on the top this time because that's what I'm converting to. And again, I don't want moles of hydrogen, I want grams of hydrogen, so moles of hydrogen goes on the bottom. I'm going to use the molar mass of hydrogen to figure out the grams of hydrogen. Again, molar mass in front of moles is 1. And again, in front of hydrogen chloride, I want to use 3 significant figures. So remember that was 35.5 for chlorine and 1 for hydrogen. So we calculated that already. One's to be 36.5. In our mole ratio, remember our coefficients become our numbers in front of moles. So our coefficient on hydrogen was 1, and on hydrogen chloride it was 2. Molar mass is 1, and again we have 1.0079, and there's 2 hydrogens, so we get 2.0158. So I'm going to use 2.02 because I want 3 significant figures. So then in my calculator, right, I'm going to do 6 times 2.02. I'm going to divide that. I'm going to need parentheses, 36.5 times 2. So 6 times 2.02 divided by 36.5 times 2. And again, okay, I want to use 3 significant figures. So my calculator gave me 0.166027397. So with 3 sig figs, 0.166 grams of hydrogen. So again, remember when we're calculating limiting reagents, I've always shown you 2 different options. You would never do both. You would only choose one or the other. And you always have to use your limiting reagent to calculate the amount of any product. So that's where we're going to stop for today. Thank you and have a great day. I'll talk to you tomorrow.